back into class here, lesson 10.3. We're going to be talking about arcs now. We've mentioned arcs. You've been exposed to them somewhat. This arc here is a minor arc because it is less than half of the circle in the fractional part that it takes up. Now this would be a major arc because I've gone over the 50% mark of the circle. So hopefully you've recorded some definitions already and put them in your green books. There was a PowerPoint on Moodle. You didn't need to use it. You could have just recorded the definitions out of the textbook. But I'm going to be using vocabulary that I'm assuming that you know from that. Okay, we're going to be looking at arcs. Arcs have two different important measurements. One we would simply call the measurement of the arc, and that is given in degrees. Let's hide the length for now. Okay, so this measurement is in degrees here, and you can expect here 180 degrees would be halfway around the circle, all the way to an arc that measures 360 would be the entire circle. And then we have fractional parts of that. 90 degrees would be about there. As you can see, that would be 1/4 of the circle, so on and so forth. But this arc also has a length as well, and there's the length. Written in units are in centimeters. This is 4.3. And you can see here that I can have lengths that grow, and my length could be as large as the circumference of the circle. Now, what is the dependence of these? So, does length depend on arc measure? Does arc measure depend on length? We see that they both seem to be growing together. However, I'm going to show you that I can grow the length without growing the measure. Okay, so if you want to notice what's going on now, as I make this circle large, my length is growing, but it's still 118.5 degrees. Let me use an easier measure that's easier to see. Let's go 90 degrees. So 90 degrees we understand to be 1/4 of the circle. You can see that the shaded part is 1/4 of the entire circle circumference, and as I make it small, it's still 1/4, still 1/4, still 1/4, but that length is shrinking. So if we now talk about congruent arcs, which is what we want to address and we'll be using, what's it take to have congruent arcs? Well, I can create arc lengths that are the same. I'm going to try to do that. I'm going to try to make these two lengths the same. So I'm going to shrink this one up until it's 3.8, 3.87. That's as close as I'm going to be able to get. And notice that, well, I just missed that up. Take that back to 3.88. There we go, 3.88. Notice we have the same length there, but we would not say that these two arcs are congruent. And you can imagine if I laid them on top of one another, they would not match one another perfectly. And we can see, here's the reason, that our arc measures are different. Our arc measures are different even though our lengths are the same. If I could pull that over, that's going to move on me. You can see here. Try to arrange this circle a little bit. Those arcs are never going to be able to match unless I'm dealing with a circle that has the same, is the same size. So the moral of the story here is that arcs can have the same length. We can have the same length, but not have the same arc measures. Okay? And we can have the same arc measures. We can have the same arc measures, but not the same length. Case in point, let's go to that 90-degree arc. So I've got that 90 degrees, and I can move this one over to 90 degrees as well. You get the picture. And clearly those lengths are not the same. In order to have congruent arcs, we must have the same measure and the same length. Let's move on. So today, in today's lesson, we are going to be really looking at how arcs, chords, and central angles correspond and relate to one another. Clearly there is a relationship. You can see here as my central angle, as I pull my central angle wide, my chord is growing and also my arc is growing. So we're going to be looking at the relationships between these. If I've got congruent arcs, what does it mean about their corresponding chords and their corresponding central angles? This is this arc, chord, and central angle form somewhat of a pact. The central angle here intercepts the circle at these points B and E, and that creates this chord and also creates arc BE. Creates that arc right there. So the arc, chord, and the central angle all are being created together. And so we want to look at those together. So I've colored it here. I've got one circle here because we want to look at how if I've got central angles that if I understand know my central angles, does that mean I know something about these arc measures? And we're going to look at 6 different theorems, and I know that seems overwhelming, but it's really not, because you'll catch on very quickly on their relationships here. But let's start with I'm going to create congruent central angles here. So we're going to look at congruent central angles. 61.81. I'm pretty close now. Let's see if I can get that closer. 61.61. That might be as close as I can get. We're going to assume now that these central angles are congruent. If these central angles are congruent, what does that allow me to conclude about either my arcs or my chords? Let's choose one. Let's go with my arc measurements. Let's take a look at my arc measurements. My arc measurements happen to have the same measure and the same length. 4.1, 4.1, measure 61.6, 61.8. That's pretty close. Therefore, these arcs are congruent. The arcs are congruent. So, to summarize that, if central angles are congruent, then corresponding arcs are congruent. That's what we notice. Now notice this is coming out of the same circle. So if I've got the same circle or congruent circles, this is going to be the case. Let's take a look at some of the other givens. Let's suppose I have chord measurements. Let's start with chord measurements. So FD is this chord here. It's 3.91, and this one is 3.91 as well. So the chord measurements are the same. So what we basically notice is this. I'll just cut to the chase. If my central angles are congruent, if these are congruent, then my arcs are congruent. If my arcs are congruent, then my chords are congruent. Okay? Or if I know that my chords are congruent, then I can conclude that my arcs must be congruent. And that also means that my central angles are congruent. All of this is true within the same circle if these relationships exist. So let me write this like this. if I have chords congruent, that implies I've got central angles congruent, which implies that I've got arcs congruent, which implies that I've got chords congruent, and it works in the opposite direction as well. If chords are congruent, then arcs are congruent, and if arcs are congruent, then central angles are congruent. Central angles congruent, then chords are congruent. So this is somewhat the picture of the lesson. Let's look at the theorems more exactly. So the first two theorems are stated this way, and you can look at the colors to help the given and the response. Given, if two central angles of a circle or congruent circles are congruent, so notice in blue we've got central angles. These two central angles are congruent. What do I conclude? Then I conclude then that these interceptor arcs are congruent. Notice that this is simply a biconditional statement. So theorems, these first two theorems are biconditional. Now let's look at number 2. It's going in the opposite direction. Notice the change in colors. If two arcs are congruent, now what's blue is my arcs. Blue arcs are congruent, then I can conclude that my central angles are congruent. Next two theorems are going to be similar. If two central angles of a circle are congruent, so I've got central angles. Now I've shown two separate circles, but they are congruent. Notice this disclaimer here, or congruent circles. So it works if I'm dealing with, if it's of a circle, I'm dealing with two central angles, these pairs of figures within the same circle, or it also works when I've got two congruent circles. Okay. So here I've got central angles are congruent. What do I conclude? In red, I've got congruent corresponding arcs, or chords, I'm sorry. So I'm showing chords. Again, this is biconditional with number 4. It just says now if I've got chords congruent, I start with chords congruent, then their corresponding central angles are congruent. And last of all, 5 and 6. Now we have arcs. If two arcs of a circle are congruent, or congruent circles, I'm just showing the one case here that in the one circle. So if I got two arcs in the same circle that are congruent, then I can conclude that their corresponding chords are congruent. Biconditional, number 6. I'm starting with the chords and say that those chords are congruent. Then I can conclude that their arcs are congruent. Again, summarizing those 6 relationships between these 3 different parts of a circle. Let's move to some examples. Okay, so now we're going to look at the first example, which is arcs. What fractional part of a circle is an arc that measures 60 degrees? So, here's my circle here. What fractional part of a circle is an arc that measures 60 degrees? So if I take this and I write the measure at 60 degrees, That's pretty close to 60 degrees. What fraction of the circle is this? What fraction of the circle is this? Well, what I can do then, if I want to know what fraction of the circle, this is 60 degrees out of, all of this is 360 degrees. So what fractional part would be 60 degrees out of 360 degrees, and that is 6 out of 36, or 1/6. The arc is 1/6 of the circumference. Now notice this is arc measure. Arc measure. It did not ask for length. I don't have enough information yet to know length. What I would need to know in order to find the length is I would need to know the dimension of this circle. So if I knew what this radius was, then I would be able to calculate the circumference, and then I would know it's 1/6 of that circumference. So length is pretty easy as well, but I would need to know some more information about my circle. Let's try example 2. Find the measure of an arc that is 5/9 of the circle. Okay, so I'm dealing with an arc here. I want to be 5/9. So what is this measure now? I'm going in the other direction. And I know the fractional part is 5/9. Well, 5/9 is a little bit, just in our head, 5/9 is a little bit over half, isn't it? So we know that our measure is going to be over 180 degrees because it's 5/9 of the circle. So what we're taking now is 5/9 of 360. 5/9 of 360 degrees. And that, what is that? It is over 180, and it is 200 degrees. Right? So if I adjust now this to 200 degrees, there's 200 degrees approximately. That is 5/9 of the circle, and it looks like it. It's over half, slightly over half. 5/10 would be half, so 5/9 is slightly over. Let's look at a proof example. Example number 3. Segment AB is a chord of circle E, and C is the midpoint of arc AB. Prove that ray EC is the perpendicular bisect of chord AB. Well, let's construct this. Okay? Segment AB is a chord of circle E. So I've got a circle that I'm talking about. So here's my circle. I've got a segment which is a chord. That chord is called AB. There's A. There's B. C is the midpoint of this arc. So C is the midpoint of this arc. So I'm going to construct this arc. On Geometry Sketchpad, you can construct the arc by highlighting 3 points, going up to construct, and down to arc through 3 points, and it's constructed there for you. I like to give it a little bit of color so that we can see it. Okay, there's our arc. I want to find the midpoint, and I can construct the midpoint, I believe. No? Thought I was able to do that. Construct a midpoint. That's alright, we don't need to. I'll pencil one in. The midpoint looks like it's approximately right here, and we're calling that point C is the midpoint of arc AB. said that the center of the circle is point E, because this is circle E. Alright, prove that ray EC. So let's draw a ray through EC. There's point through EC. We want to prove that that is the perpendicular bisector of AB. So I'll mark in red what it is we wish to prove. We wish to prove that it's perpendicular and bisector. Okay, now I'm going to erase those markings so we don't confuse them for what is given. Those are not given. What is given? We're given in blue, we're given that this arc is bisected, and we have a chord. So what is some auxiliaries that we can draw here to make this more clear? Well, a very common auxiliary are these radiuses. See? Let's look at these two radiuses here. How is that helpful, and how are the theorems from this section helpful? Well, we've got two central angles. We've got a central angle here that must be congruent with a central angle here. Now, why is that the case? Well, because the chords that they're intercepting are congruent. Those two chords are congruent, therefore their corresponding central angles are congruent as well. Alright, well, how is that helpful? Well, now I've got, by reflexive, I know that this segment here is congruent to itself. And I've got radii are always congruent. The radiuses are congruent of the same circle. Looks like I've got side, angle, side to show that those two triangles are congruent. And now that we know the triangles are congruent, we know now that we have that chord has been bisected. Those must be congruent. So to write this up a bit, our proof would look like this. Statements and reasons. First, the givens. We'd state the givens. I'm gonna run out of room, so I'm gonna leave that go. Number two, what do we notice here? We draw in EB and EA exist because 2 points determine a segment. Since those are both radii, we know that EB is congruent to EA because radii of the same circle are congruent. Number 4. Let's name this point here we'll name this point here F. We know that EF is congruent to EF by reflexive. Number 5, we know that angle AEF is congruent to angle BEF. And that came from this lesson. If chords are congruent, then corresponding central angles are congruent. Number 6. Now I'm ready to say that I've got congruent triangles. Triangle AEF is congruent to triangle BEF. My reason? Side angle side. Number 7. Now I know that AF must be congruent to FB. Those two must be congruent by CP, CTC. Finally, number 8. If those are congruent, we know that the chord is bisected. Definition of bisect. Now we have one last thing to prove, and that is that it is perpendicular. So we'll come over here, and we'll finish this over here. Number 9. Number 9, we can say now that angle AFE is congruent to angle BFE. We know that by CPCTC. Number 10, angle AFE and angle BFE are right. Congruent and supplementary angles are right, and therefore perpendicular. Right angles are perpendicular. We have proven what we wish to prove, and that is a perpendicular bisector. So there's an application of the theorems from the lesson. All right. So with that, I'll sign off, and we'll see you in class tomorrow.